So how do we do it? We average. For position, we start every place in the state space and study evolution. We start at any point. For time, what we do is we average, and we find it convenient to average in a Laplace transform way. And this, you will sooner or later understand, is an example of a character. It's a character that's appropriate when you're studying symmetries forward in time. And now, do we have a symmetry forward in time? If you look any place on a trajectory, where we are depends at the time we are, and at every point this law of evolution is different. So if you just look at trajectories, there's actually no obvious time invariance. However, if you integrate over entire trajectory, then by definition we have time invariance because we have integrated over all time. So a very simple version of time invariance is that, but as I'll show in a second, and I've shown it already before, but I want to emphasize it in this more group theoretic way of thinking. It turns out that if you have a compact invariant object, in particular equilibrium of periodic orbit or invariant curves, it suffices to integrate over one period of that object. That means that we can actually express our calculation, our average in terms of time invariant compact objects, and compute it in finite time, but are time invariant. Whereas any piece of trajectory depends on where we start and where we end and what the evolution law is on the trajectory, meaning what the velocity, tangent velocity that we're integrating is along the trajectory. So everything is time dependent. My point is, if there is a symmetry, that means that many calculations that we do, if they're related by symmetry operation, they're identical calculations, so they don't need doing. The thing to do is, if there is a symmetry, you also average.